How do you prove Euclidean theorems using only axioms? Imagine building a giant puzzle where every piece fits perfectly because you follow a set of simple rules. That's how Euclidean geometry is proved using only axioms. These axioms are basic statements we accept without proof, like a straight line can be drawn between any two points. They are the foundation of everything else we prove in geometry. First, we start with these axioms and some undefined terms, such as point, line, and plane. These terms are like the building blocks of the puzzle, but we don't define them in complicated ways. Instead, we accept their basic properties, like a point has no size or a line extends forever in both directions. The axioms include things like a circle can be drawn with any center and radius, and all right angles are equal. One special axiom, called the parallel postulate, says that if two lines are cut by a transversal and the interior angles on one side add up to less than two right angles, then the lines will meet on that side. Once we have these starting points, we use logical reasoning to prove new truths called theorems. Logic is like a set of rules that tell us how to connect ideas. For example, if we know that two angles are alternate interior angles when a line crosses to others, we can use that to prove that two lines are parallel. We do this step by step, making sure each move follows from the axioms, previous theorems, or accepted rules of logic. Sometimes, to prove a statement, we assume the opposite and show that this leads to a contradiction. This method is called proof by contradiction. If assuming something false leads to an impossible situation, then the original statement must be true. It's like solving a mystery by eliminating false clues. As we prove more theorems, they become tools for proving even more complex ideas. For example, once we prove that the angles in a triangle add up to 180 degrees, we can use that to prove other facts about shapes and angles. Each proof is a chain, starting from the axioms and building up step by step, ensuring every link is solid. This process keeps geometry precise and reliable. Every shape property, length, and angle measurement can be traced back to the original axioms. It's like constructing a house where every brick is carefully placed according to strict rules. This method of proof guarantees that all geometric truths are based on simple, accepted principles, making Euclidean geometry a trustworthy system.